Well, good day, ladies and gentlemen, and welcome back to Chem. We are in our unit on gases, and let's take a look at what we have to consider here. It says consider nitrogen gas at 27.25 psi. What's psi? And what is the pressure at ATM? Okay, so we're doing something with pressure. Well, let's go back and let's do a quick review and see if we can learn something about pressure, right? Yikes, it doesn't help us. Let's go with black. We have gases, right? And we say, hey, gases are a state in which there is no, what? Definite volume and no definite shape. Okay, so that's kind of a definition. And then we talk about the kinetic theory, which is our way of it. This explains what? It explains gas behavior based on the movement of gases. Good. So that's what we use to do a lot of predictions. And there are 5 assumptions here, right? Assumptions. And we said, hey, one is that there are a large number of tiny particles far away from each other, right? Number 2, they are in continuous, rapid, random motion. What? There are no forces of attraction between gas particles. That gas particle collisions are elastic, and that temp, and this is very important, right? Temp reflects what? Average kinetic energy of my particles, which is equal to 1/2 mv squared, where m is mass and v is velocity. So what does this really mean? Temp, if my mass is not changing, reflects the velocity of particles, so that when my velocity equals 0, meaning when I have no movement of my particles, then we say that we are at absolute 0, and that's in the Kelvin scale. Good. And then we started talking about pressure, and we said, hey, in general, pressure is what? Force per area. But we said for gas pressure, it's really something different. Pressure for gases represents what? Collisions of gas particles against the wall of my container. And when we take this idea and we take this temperature idea, we can start making some predictions, right? That if my volume goes down and everything else stays constant, then my pressure is going to go what? Up. And if my temp goes up and everything else stays constant, then my pressure is going to go up. Because my particles are flying around faster, that means they're colliding more. If I add more moles, if I add more gas particles, well, I have more particles, that means I'm going to have more collisions, and my pressure is going to go up. So we can get all these, we can get these kinds of relationships just by thinking about this and that, right? Now, let's get into a little more on pressure, and let's actually talk about some calculations, pressure calculations. So pressure calcs. Yes, pressure calcs. And, or conversions, really. We're going to start off here with, I guess, calcs conversions. Maybe we'll call it conversions. Conversions is probably better than calcs. Good. And so we need to know what are some units for pressure. Well, my units are things like I can have 1 atmosphere. Atmosphere, that's a unit of pressure. PSI, well, that means what? Pounds per square inch. You know, that's what we use in engineering a lot. It's an English unit. We can have kilopascals, kPa, that is a kilo Pascal, right? We could have millimeters of mercury, which is just the height of a column. millimeters of mercury. That means I have a column that has so many millimeters of mercury in it. Millimeters of mercury. Mercury. Good. And I can have torr. And torr is really for Torricelli. Torricelli. He's some guy who did stuff with barometers. And that's really equal to, well, we'll just leave it at that. So those are our typical units, right? Atmospheres, PSI, kilopascals. What are my conversions in? Well, 1 atmosphere equals 14.7 PSI, which is equal to 101.3 kPa, right? Which is equal to 760 millimeters of mercury, which is equal to 760 torr, which means what? 1 millimeter of mercury equals 1 torr. There we go. And then we just have to start playing around with our units the way we would with dimensional analysis. So if I said, hey, I have a gas that has 0.72, 72 atmospheres, and I want to know how many millimeters of mercury. What am I going to do? I'm going to say, okay, I've got, let's go up here, 1 atmosphere per 760 millimeters. So I'm going to say 760 millimeters per 1 atmosphere, right? What goes on the bottom? Well, I want to get rid of my atmospheres. What goes on top? What I want. And then I'm going to take my calculator and I'm going to take 0.72 times 760 and I get 547.2, and I want to round it to 2 sigs. So let's say I'd have 550 millimeters of mercury. That's how that dog works. Excellent. Now let's go to this question. I have 27.25 psi, 27.25 psi, and I want to know atmospheres. So what am I going to do? I'm going to put atmospheres on top and psi on the bottom. What's my relationship? Na 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 na. Atmospheres. Na 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 na. What? Okay, I have 14.7 psi to 1 atmosphere. Okay, good. Na 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 na. 14.7. So I'll take my 27.25 times 1 divided by 14.7. And what do I get? I get 1.853, but how many sigs? I can get 3 sigs out of this. So that would mean I have 1.85 atmospheres are equal to 27.25 psi. What is its pressure in millimeters of mercury? Okay, so we start off with 27.25 psi, and I want to get to millimeters of mercury. And what do we know? Okay, let's go back up to our we wanted to go from what? Millimeters of mercury. Here's millimeters of mercury and psi. And so what's my relationship? It is 14.7 psi, 760 millimeters of mercury. Here we go. So 760 millimeters of mercury over what? 14.7 psi. Okay, 27.25. Okay, got that. Times 760. Got that. Divided by 14.7. Yee! And what do I get? Ooh, looks like a gigantic number. 1408. Could that be right? Well, I think so. 760, yeah, so looks good to me. And how many sig figs? 3 sig figs here, right? So this has to be 1410 millimeters of mercury. Sounds cool? I think it's cool. All right, you guys do the next one. Bring me back when you're ready. Well, this should be a piece of cake, right? I have 1.22 atmospheres. 1.22 atmospheres, and I want to convert between atmospheres and torr. So I go back to my equalities, right? Torr and atmospheres. So it's 1 atmosphere to 760 torr. So 760 torr per 1 atmosphere, and so I have 1.22 times 760 divided by 1, and so that's 927. 927. By the way, this is, we could go with 1.00. This is a definition. 1 torr equals 760 point. Okay? Good. So 927, what? Torr. So yeah, don't let this 1 change your sig figs. Cool. What is its pressure in PSI? Okay, 1.22 atmospheres times what? 14.7 PSI per 1 atmosphere. Yoink. And I have 1.22 times 14.7, and I get 17.9. 9 PSI. Hey, that's a piece of cake. Yeah, it's really simple. Very simple. We can go all over the place with these units. Cool. Moving on. Consider a mixture. Okay, a mixture of hydrogen and nitrogen gas. Okay, in a rigid tank. Okay, that means it's not going to expand. The pressure caused by only the hydrogen is 0.375. The pressure caused only by the nitrogen. Okay, so I figure out that I have some different pressures going on here. What is the partial pressure of hydrogen? What is the total? What is the partial pressure of nitrogen? What's the total? I think we need some notes. Yes, we do. And we want to come down here and we want to talk about something else here that's related to pressure. And I'm going to have to bring it down around our conversions. And we want to talk about Dalton's law of partial pressure. Partial pressures. There we go. And what does Dalton's law of partial pressures state? It states that the total pressure of a mixture of gases is the sum of the pressures which each gas would produce if it were alone. Okay, cool. Now, let me tell you, this is a little wordy. It's much simpler when we just look at it. I've got a container here, right? And let's say I have some oxygen gas. We'll go with blue for oxygen gas. And let's go with some green. We'll call that nitrogen gas, right? Okay, what's going to happen? Well, the nitrogen gases are going to bounce off the wall, right? And so they're going to create a pressure, right? Because whenever I have collisions against the wall, I get pressure. So I'm going to have a pressure related to the nitrogen, right? But not only do the nitrogen gases bounce off the wall, but also my oxygen gases bounce off the wall, right? So what happens? Then there is also a pressure in this container associated with my oxygen. Now, what's the total pressure? Well, the total pressure is going to be the pressure caused by all of these molecules, oxygen and nitrogen, bouncing off the wall. Yoink, 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 zoink, boink. All of those things are bouncing off the wall. So what's my total pressure equal to? Total pressure of the pressure of my mixture of gases is going to be equal to the pressure that nitrogen makes alone or would make alone plus the pressure that my oxygen would make alone. That's Dalton's gas. So if I have Dalton's law of partial pressures. So if I have a mixture, of gas 1, gas 2, and gas 3, then what's the total pressure? The total pressure would be the pressure caused by gas 1 plus the pressure caused by gas 2 plus the pressure caused by gas 3. And what do you suppose we call each of these pressures? We call these the what? This is the partial pressure of gas 1, which means it is the pressure which gas 1 would produce if it were alone. And this would be the partial pressure of gas 2. So it would be the pressure which gas 2 would produce if it were alone. And how does it produce it? By those collisions against the wall of the container. So let's take a look at this. The pressure caused only by hydrogen is 0.37. Okay, so I have a mixture, and in there I have some nitrogen and I have some hydrogen, and it says that if the hydrogen creates a pressure by itself, it would be 0.375 atm. The pressure caused only by the nitrogen is 8.22 atm. Okay, good. So what's the partial pressure of the hydrogen? Well, that's easy. That's the pressure which is caused by the hydrogen. Wow. Do we have to even do any calculations? No, we don't. We just rewrite down our 0.375. What's the partial pressure of the nitrogen? 8.22. Hey, I like this kind of calculation, Mr. Smith. Yeah, this is easy. Hey, chemistry is easy. What's my total pressure? My total pressure is going to be what? The pressure of my hydrogen plus the pressure of my nitrogen. So that would be 8.22 plus 0.375. Zoink. And let's add these. I get a 5, I get a 9, I get a 5, I get an 8. Watch our sig figs. So I have to get rid of this 5 because it's not significant. I round up. And so I'd get 8.60. What? What are my units? Units. ATM. Zoink. There we go. Not bad. So you guys give it a try. There. Consider a mixture of carbon dioxide, water, and hydrogen sulfide gas. Good. You guys bring me back when you're ready. Okay, they tell me the total pressure. Okay, so I know that my P total is equal to 0.997 atmospheres, right? And what makes up that P total? Well, I have some H2S gas in here, and I have some CO2 gas in here, and I have some H2O gas, right? And they're all bouncing off the walls like some of my students right at this moment, right? They're bouncing off the walls if they've had some dum-dums to eat today. And so what's my total pressure going to be? Well, it's going to be the pressure caused by my CO2 plus the pressure caused by my H2S plus the pressure caused by my H2O. And notice, we're talking about H2O gas, not liquid. The liquid would not cause the same kind of pressure, right? Cool. Now, what do they give me? They give me the total pressure. So I know that I have 0.997 atmospheres, and that's equal to what's CO? Here's CO2. What do we don't know. We don't know the pressure of CO2. Okay, so I don't know that. Do I know the pressure of hydrogen sulfide? The partial pressure of water and H2S are blump respectively. That means what? That means this 0.247 goes with the water, and this 0.229 goes with my H2S. So 0.229 atmospheres plus what's my water? 0.247 atmospheres. And so then what is my pressure? What's the pressure of my carbon dioxide? I think we can do this without a calculator. First of all, let's take 0.229 and I'm going to add it to 0.227. 0.247, right? So this is 6, carry the 1, 6, 7, and 4, 0.476, okay. And then we're going to subtract that from 0.997 minus 0.476. I get a 1, I get a 2, I get a 5, 0.5, woohoo, 0.521 atmospheres. And that would be my correct answer. Cool. All right. That would be it. By the way, sometimes it's really good just to do math without your calculator. Next time you go to the store and you get like 20% off, hey, do that without your cell phone. Do that without your calculator. Do it in your brain. It makes your brain really happy, and you'll be a better student for it. Okay? So that will be it this time. We'll catch you next time. Ciao, Belle.